Hello everybody. In the previous lecture, we looked at performing mechanical energy balance calculations. In today's lecture, we will actually perform more example problems so that we can familiarize ourselves with how to calculate mechanical energies and how to perform balances for mechanical processes. So, this will be a tutorial session on this topic. Let us first start with the first problem. Here is the first example problem. Water flows from an elevated reservoir through a conduit to a turbine at a lower level and out of the turbine through a similar conduit. At 1, which is the point 1, the pressure is 207 kilopascals, and at point 2 the pressure is 124 kilopascals. What must be the water flow rate if turbine output is 1 megawatts? So, the setup is given. So, you have point 1 which is at an elevated level. From here the water flows down to the turbine and then it again falls back to the second point. So, you have an initial drop of 100 meters and the second level of drop is 3 meters. You also have been given that the shaft work is 1.00 megawatts. So, having this information, let us try to perform mechanical energy balance calculations. The general equation for the mechanical energy balances can be written as delta P divided by rho plus G delta Z plus delta U squared by 2 plus F cap equals minus Ws dot divided by m dot. So, this would be the general mechanical energy balance equation. In this system, we can ignore friction factor because there is no friction factor which has been provided to us. However, we cannot ignore shaft work. So, we can also ignore change in velocity because we have not been given that the conduit is changing in diameter. We have been told that the conduits are similar, which means we can assume that their cross sections are the same, which would indicate that the linear velocities would also be the same. So, the equation here simplifies to delta P divided by rho plus G delta Z equals minus Ws dot divided by m dot. The shaft work has been given as Ws dot equals 1 megawatt, which is equal to 10 power 6 Newton meter per second, and we have been told that the pressures are given for point 1 and point 2. So, delta P would be final pressure minus initial pressure, which is 124 minus 207, giving a value of delta P as minus 83 kilopascals. So, this can be written as minus 83 times 10 power 3 Newton per meter squared, and density is the density of water, which would be 1000 kilograms per meter cube, and G, which is acceleration due to gravity, would be 9.81 meters per second squared, and delta Z, which is the total change in height, would be equal to minus 103 meters. With this, we can actually substitute all the values back into the equation for mechanical energy balance which we had. So, which is delta P divided by rho plus G delta Z equals minus Ws dot divided by m dot. So, delta P we had calculated as minus 83 times 10 power 3 divided by density, which is 1000. So, the units would be Newton per meter squared divided by kilograms per meter cube plus G, which is 9.81 times delta Z, which is minus 103. So, the units would be meters per second squared times your delta Z is again meters. The term on the right hand side is minus Ws dot divided by m dot. Our minus Ws dot has been given as 1 times 10 power 6 Newton meters per second divided by m dot, which would be in terms of kilograms per second. In this equation, you can verify if the units are correct. Just try to substitute the actual values which are the basic units from SI units for Newton and Pascals, and confirm that the units for individual terms are correct. And if you do that, you will finally end up with m dot as 915 kilograms per second. So, when 915 kilograms of water flows through the turbine per second, you would be able to generate 1 megawatt of shaft work. So, with this we would have solved this problem. Let us look at another tutorial problem to help us fully understand and get into the habit of solving mechanical energy balance calculations. In this problem, we have been given a mixture which contains glycerol and water, and we have also been told that the volume of this mixture is 1000 liters, and we need to finally prepare a mixture which would be containing 60% glycerol instead of 95% glycerol. So, for identifying how much would be the mass of each of these components which have to be fed, we first need to know the density of these mixtures. We only have the volumes and we have the densities for the pure components. So, the first step for this problem would be to calculate the density of the mixture, so that we can get the mass of the mixture which is being fed. So, for this we first need to make a simple assumption. The assumption would be the volume of the mixture would be equal to the summation of the volumes of the pure components. By that, what I imply is, when two things are added, glycerol and water are added, there are no interactions which results in change in volume, or in other words, volume is additive. With that assumption in mind, let us first try to calculate the density of this mixture, so that we can calculate the mass of the mixture. To calculate the density of the mixture, well, let us first calculate for the 95% mixture. For calculating the density of the 95% glycerol mixture, we will assume a basis of 100 kilograms of mixture. So, this 100 kilograms of mixture will contain 95 kilograms of glycerol and 5 kilograms of water. We know the densities of glycerol and water, those values have been given to us. So, this 95 kilograms of glycerol would actually occupy 95 kilograms divided by 1.26 kilograms per liter of glycerol. So, this would be the volume, because this is mass divided by density. So, this value would be equal to 75.4 liters of glycerol. So, what this means is 75.4 liters of glycerol would weigh 95 kilograms. Similarly, 5 kilograms of water would basically occupy a volume of 5 liters of water. So, with this we know that the total volume of the mixture would be equal to 75.4 plus 5, giving you 80.4 liters as the total volume of the 100 kilogram mixture. So, from here we can calculate the density of the mixture as mass of the mixture, which is 100 kilograms, divided by volume of the mixture, which is 80.4 liters, giving us the density as 1.24 kilograms per liter. This implies that 1000 liters of mixture which is fed would actually weigh 1000 times 1.24, which is equal to 1240 kilograms of mixture. So, the process flow chart would look something like this. You would have 1240 kilograms of 95% glycerol, 5% water coming in. You also have M1 kilograms of 35% glycerol, 65% water coming in through a pipe with an inner diameter of 5 centimeters. So, the final flow stream is, let us call it M2 kilograms, and this contains 60% glycerol and the rest 40% is water. Now that we have calculated the mass of the mixture which is coming in, we can now perform simple material balance calculations to identify the mass of 35% glycerol which needs to be fed and the mass of 60% glycerol which will be produced. So, for that we can write a total mass balance which would be 1240 plus M1 is equal to M2. We can also write a glycerol balance which would be 0.95 times 1240 plus 0.35 times M1 is equal to 0.6 times M2. So, you have two equations and two unknowns, you can solve for M1 and M2. So, the value for M1 would be equal to 1740 kilograms and the value for M2 is equal to 2980 kilograms. The problem requires us not just to calculate the mass of 35% glycerol and 60% glycerol final solution, it has been asked that we calculate the volume of the final mixture which is 60% glycerol. For that we need to know the density of the final solution. So, using the same techniques which we did earlier, we will be able to calculate the density of the final mixture which is 60% glycerol. So, what you would do is again assume a basis of 100 kilograms of 60% glycerol. So, this would be the basis for calculation of density. The 100 kilograms of 60% glycerol would contain 60 kilograms of glycerol and it would also contain 40 kilograms of water. So, the volume occupied by 60 kilograms of glycerol would be 60 divided by density which is 1.26 and 40 kilograms of water would occupy a volume of 40 liters of water. So, the volume of 60 kilograms of glycerol would be equal to 60 divided by 1.26 which is 47.6 liters. So, the total volume would be equal to 87.6 liters. So, your density would be equal to 100 kilograms divided by 87.6 liters, giving you a final value of 1.14 kilograms per liter. So, using this we can calculate the volume of the 60% glycerol product. So, we have the mass and the density. So, volume would be mass divided by density which is 2980 divided by 1.14, giving a final volume of approximately 2610 liters. The next part of the problem expects us to perform the mechanical energy balance calculations. What are the information that we have regarding the mechanical energy balances? We know that there is a pump which needs to deliver the liquid at a height which is 23 meters above the point at which it is being discharged. The problem statement tells us that the pipe discharges the liquid 23 meters above the liquid level, which means this is the liquid level. Let us call this as point 1, and from here the discharge happens at a height of 23 meters above the liquid, and the discharge happens through a pipe which is 5 centimeter inner diameter, and the friction factor is equal to 50 joules per kilogram. We also know that at points 1 and 2 the pressure is 1 atmosphere. With all this information, let us write the general mechanical energy balance equation and solve for the shaft work that needs to be delivered. So, we have delta P divided by rho plus G delta Z plus delta U square by 2 plus F cap equals minus Ws dot divided by m dot. As pressure change is 0, the first term can go to 0. You would have G delta Z, where delta Z equals 23 meters, and we need to calculate delta U squared. So, we have the diameter of the pipe. Using that we would be able to calculate the velocity at the point of discharge. We can assume that the velocity of liquid which is in the storage tank would be 0 because it is a stationary liquid in a tank. So, that means we just need to calculate the velocity at the point of discharge. Friction factor value has been given to us. So, we can actually substitute all these values to calculate the shaft work. To calculate the linear velocity at the point of discharge, we have the diameter of the pipe, which means we can calculate the cross section of the pipe, cross sectional area of the pipe. And using the volumetric flow rate, we will be able to calculate the velocity which is the linear velocity. Volumetric flow rate divided by cross sectional area will give you the velocity. To calculate the volumetric flow rate of the 35% glycerol solution, we need to know the total volume of the 35% glycerol solution which has been supplied. We already know that the process happens in 13 minutes. So, we know the time frame. So, if we know the total volume, we can calculate the volumetric flow rate. As we already have assumed that the volumes are additive, we know the total volume of the final 60% mixture and the initial volume of the 95% glycerol mixture. So, we can calculate the volume of the 35% glycerol mixture using these two values. So, the volume of 35% glycerol mixture would be 2610 minus 1000, giving a value of 1610 liters. So, this is the volume which we are adding. We know that this is being added over a period of 13 minutes, from which we can calculate the volumetric flow rate. From the volumetric flow rate, we can calculate the linear velocity by dividing it using the cross sectional area. So, linear velocity at point 2 would be equal to 1610 liters divided by 13 minutes times 1 meter cube per 1000 liters, just for converting them to meters, and the minutes can be converted to seconds as 1 minute contains 60 seconds. So, this now gives you the volumetric flow rate in terms of meter cubes per seconds, and this can be divided by the cross sectional area, which would be pi r squared. R here would be 0.025 meters, because it is 5 centimeter inner diameter. So, which would mean it is 2.5 centimeter radius, and converting that to meters, we would have 0.025 meters. So, from this we can calculate the velocity as 1.051 meters per second. So, we can calculate delta u squared by 2 as 1.051 whole squared divided by 2, which is equal to 0.552 joules per kilogram. As we already knew the value for delta z, we can calculate g delta z as g is 9.81 times delta z is 23, giving a value of 225.6 joules per kilogram. We already know that F cap is 50 joules per kilogram. We can calculate the mass flow rate from the mass we had already calculated from the material energy balances. So, it is 1740 kilograms supplied in 13 minutes. So, in terms of kilograms per second, it would be 2.23 kilograms per second. The equation would be minus Ws dot divided by m dot is equal to delta u squared by 2 plus g delta z plus F cap. So, this would mean Ws dot would be equal to minus 2.23 times 0.552 plus 225.6 plus 50, giving a value for Ws dot as minus 0.62 kilowatts. So, the shaft work which would be delivered by the pump would be 0.62 kilowatts. So, with this we have performed different types of mechanical energy balance calculations. Hopefully, you have familiarized yourselves with performing these calculations. Try more problems along these lines, so that you are familiar with the calculation steps, and also you can understand how the concepts need to be applied. With that, I would like to thank you for today's lecture and meet you in the next class.